All right, welcome back. And now we are going to go over section C of chapter 5. So we're going to talk about statistical tables and graphs. Okay, so let's jump right in. And so these are going to be very common graphs that we've all pretty much seen, most of these. Okay, so we're going to start with the idea of a frequency table, though, because all of our graphs will come from frequency tables or relative frequency tables. So a basic frequency table has two columns. The first column lists all the different categories of data, okay, or all of the different values of the random variable x that may come up. Right? So this could be categories like shoe color, eye color, skin color, ethnic background, political party affiliation, all kinds of things. Or it could be measurements like the outcome of a roll of a die, or it could be the number of pairs of shoes that you own, or the number of drivers on an auto policy, things like that, or it could be the height, right? So those are the kinds of things that we talk about when we talk about frequency tables. The second column in the table is going to be the frequencies, of course, right? So the number of objects, people, subjects that fall into any one of those categories. So now relative frequency is it's a percentage, really. Most of the time it's represented as a percentage. So it's a proportion, right? We want to find out what proportion of the data falls into a particular category. This is what we look at when we look at relative frequency, right? And so how do you calculate it? Well, you're just finding the proportion of the total frequency that falls in a particular category. So you're going to take the frequency of that category and divide by the total frequency, right? We also call the total frequency sample size. So it's a fraction, right? So a fraction, decimal, but most of the time it's represented as a percentage because percentages are very easy to understand. Then there's cumulative frequency. Now, the cumulative frequency of any category is the number of data values in that category and all the preceding categories. So it's, in other words, it is a running sum. It is a running total, okay? So as you go down the table, the cumulative frequency keeps adding the frequencies from the top going down. Now, the types of data that we're going to look at, because one of the things that I alluded to is when we were talking about dealing with the height, right? Or you're dealing with a range of values. We're going to have grouped frequencies, right? We're going to have these bins or classes, if you will. So the qualitative data consists of just values that are placed into non-numerical categories. So there's no classes per se because it's all in different categories, right? So each bin represents one and only one category, right? So quantitative data represents counts or measurements. So this is the one where it could be a count value, like in the number of pairs of shoes you own, the number of children per family, the number of family members in a household, things like that. They're countable, okay? Versus a measurement, which would be like temperature, things that you measure out, distance, things like that. Now, when you're dealing with quantitative data categories, it is often useful to group things into classes or bins. This happens when your range of values is large, right? So, and you don't want to have a whole bunch of bins, so we group them into grouped frequencies or grouped classes, okay? So each bin represents a range of values instead of just one particular value. So now, so the thing is we're going to classify each of the following types of data as either qualitative or quantitative. Okay, so now brand names of shoes in a consumer survey. Now this is not something you would measure or count, right? This is a brand name, right? So this is a quality, right? Or an attribute. When you talk about brands, that's an attribute or quality of the shoe. So in this case, it's a qualitative data, right, that we're collecting. It's non-numerical, qualitative. Okay, heights of students. Well, that is numerical, right? So it's quantitative. Okay, so far so good, right? Now let's see. C is audience ratings of a film on a scale of 1 to 5, where 5 means excellent. Now you got to be careful with this one because you may be tempted to say, oh, this is numerical, so it's quantitative. But it's not. This is qualitative because the numbers really don't mean anything other than like a scale, like a rating scale in this case. So it's a scale from 1 to 5. The numbers really don't mean anything in particular other than just a placeholder, right? Okay. And so this would be qualitative. Okay. Even though you're using numbers, it's still qualitative data because what are you measuring? You're measuring something that's an attribute, right? Somebody's rating of a film, right? Poor to excellent. All right, now let's talk about summarizing data. Now, to summarize data, there's many different ways we can do that. So we're going to consider these 20 scores on a 100-point exam. So these are 20 scores that we have. It says determine the appropriate bins and make a frequency table including columns and relative and cumulative frequencies. Now, we've got 20 scores. The range of the 20 scores, right, goes from what? 72, right? 72 to 91, 94. Okay. So we definitely want to group these. Now, in this case, the rule of thumb is binning or classes, you can have anywhere from 5 to 20 classes. No more than 20, no less than 5. Okay. So here's what they did, right? So they binned by fives. Okay. And the reason why you can see that they've binned by fives is you just subtract any two of the same endpoints or class limits, right? So these are class limits. So that's the lower class limit. These are the upper class limits. So if you subtract any consecutive upper class limit or any two consecutive lower class limits, you'll get the class width, which in this case is 5. So every class or bin has a width of 5. So that's how they determine this. Okay. So never subtract across. That'll give you the wrong number. Always subtract down the same left or right, lower or upper class limits. Okay. So then what you do is once you have your bins, in this case they have 6 bins, right? 6 classes. Now you determine the frequency. So you count which scores fall into which bins, and that's how they determined the frequencies here. And notice the frequencies all add up to 20, which they should. Okay. Always double check, make sure that everything makes sense. And then the relative frequencies is all you're going to do is you're going to take the frequencies and divide each of these frequencies by 20. Okay. So that's what they did here. 1 divided by 20 is 0.05, which again as a percentage is 5%, all the way down to 4 divided by 20, which is 0.2 or 20%. And also notice that as you add, when you add up all of the relative frequencies, they add up to 1 or 100%. And they should always do so. If they don't, then something went wrong. Okay, and again, we're not counting round off error, right? So if it's like 0.99 or 1.01, right? So that might be due to round off error if you're rounding your decimals, right? So you might end up with being a little bit off, but it should be very close to 1 or 100%. And then the cumulative frequency, Cumulative frequency is, again, you're just adding a running total going down, right? So in the first class, you've got 1 because that's all you have. So the cumulative frequency is the same as the frequency. But then when you go to the second class, the second bin, now the cumulative frequency is 3 because what do you have? You have 1 plus 2, which equals 3. And then the third class, the cumulative frequency now adds the third class to it. So it's 3 plus 3, which equals now a total running total of 6. And then if you add another 3, you get from the next class, class number 4, you get 9. And then class number 5 has 7, so you add 7 and 9, and you get a running total of 16. And notice how at the very end, it always adds up to the sample size. Okay? All right. All right, now let's talk about bar charts and pie graphs. Bar charts and pie charts. Okay, now bar charts show each category with a bar whose length corresponds to its frequency or relative frequency. Pie charts are used primarily for relative frequencies because the total pie must always represent the total relative frequency of 100%. Okay? The size of each wedge is proportional to the relative frequency of the category it represents. So if it's a 25% relative frequency, it should be a quarter of the pie, right? And so on. So here's an example of a bar chart and a pie chart looking at a distribution of grades on on an exam. Okay? Or let's say in a course. Right? So here's the frequency table. Okay? And so if you look here, we've got this bar chart. Notice the frequencies of the bars is on the left side, the left vertical axis. And then you've got relative frequency or percentages on the right vertical axis. Okay? And then, of course, the x-axis is the grade. And notice how it's discrete because you only got one grade, so it's not grouped. These are individual grades. And the height of the bars represent the number of students that got each one of the grades. Okay? And so now you can see how the shape of the distribution and whatnot. And then, of course, with the pie chart, use relative frequency, and so you know that, look, if you look at the C's, we see that 36% of the class got C's. In fact, if you add up both of the B's and C's, we see that over half the class got B's and C's, right? And if you add up the A's, B's, and C's, you can see that the majority of the class definitely got a passing grade in the class, okay? So only 8% and 12% got D's and F's. And so you can see how useful pie charts and bar charts are in and of themselves, right? So you can easily see proportions with the pie chart, right? And that's always useful. And then with the bar chart, you can see the distribution of the grades in the class. Now, here are the important labels that you want for graphs. You've got to have a title or caption, right? The graph should have a title or caption or both that explains what is being shown and, if applicable, lists the source of the data. So the caption is used to list where the data came from. Okay, and the title of the graph tells your audience, hey, what is this graph all about? Okay, vertical scale and title. Okay, so you should have your vertical axis, right? The vertical axis should be titled and it should have a scale on there so your audience knows what the tick marks mean, okay? And what the scale is. And then the horizontal axis should have a label or title and a scale as well, okay? Now, for qualitative data, The tick marks would just represent just well, they really don't matter, but tick marks would be where the category would be listed. And then a legend, if multiple data sets are displayed on a single graph, which does happen quite often, then you want to have a legend or key to identify the individual data sets. Okay, now histograms and line charts. So histogram is a bar chart for quantitative data. Okay, it's only used for quantitative data categories. The bars have a natural order and the bar widths have specific meaning. And by the way, the bars on a histogram always touch. A line chart shows the data value for each category as a dot and then connects the dots with lines. So each dot, the horizontal position, represents the value, right? And if it's grouped, then the horizontal position of the dot is centered in the bin and would represent the vertical position of the data bin, of the data value for the whole bin, right? So you could use a line graph for grouped data and data that's not grouped. And then, of course, a time series graph is a specific line graph where the horizontal axis is always a unit of time. Okay, it's always on the x-axis because time is always the independent variable. So now here's an example of a line graph and a histogram. So notice the histogram, right? So all the bars are touching, and you notice how it goes from the lowest, so all the way to the highest, right? And so we have to use boundaries. Okay, so we notice how they go. Now the only ambiguity here that I would question is at the boundary, is at the points, because again, and this goes back to the way it was defined, right? And so in this case here, oops, oh no. Here. In this case here, even there's a slight gap in between each one. 99, or excuse me, where is it at? Oh, here, 94 to 95, right? 89 to 90. So 84 to 85. So there's a gap of 1 in between. Now, if all of the exam scores are whole numbers, right, which they were, there's no issue. But what if you have half a points? So we've got to decide where those values are going to go. Okay, just something to think about. So here's a histogram. Okay, and you can see the distribution there. But also, if you look at this, this is a line graph. Notice the dots are centered at the middle of each bin. Okay, this is actually called a frequency polygon. We're not going to study those, but notice how it makes a polygon with the x-axis, right? So it makes a nice polygon. Okay, but that's an example of a line graph. Notice that the height of the dots are located in the middle of the bin, and the height of that represents the number of students in the class that got that score, okay, or got a score that's inside that bin. All right, now let's look at Oscar-winning female actors or actresses. The table shows the ages at the time that they won the Academy Award, winning actresses through 2017. So make a histogram and a line graph to display each of the data, to display each data, or yeah, to display these data, and then discuss the results. So notice we've got 32 actresses that won the Academy Award when they were in that group, 34 won in this group, and so on and so forth. So you can see how many actresses won in each age group. And notice that the age group is 10 years, right? Each class or bin is 10 years long. Okay. Now what we want to do is we're going to create a histogram and a line chart. Okay. So all we're going to do is use this table to do that. Okay. So here we go. Now this is an overlay. So notice the frequency polygon, right? So notice the frequency polygon shows the same distribution over the histogram. Okay, you can see that the majority of actresses won when they were in their 20s and 30s. And then you can also see a trend that as they got older, as actresses got older, less and less of them won Academy Awards. I believe it was for Best Actress, right? Or just Academy Award, I'm assuming. I don't know. Now the data shows that the most actresses win awards at a fairly young age, which stands in contrast of the older ages of most male winners for Best Actor. So yeah, it is best actresses. Okay. All right, so here's a time series graph. So here are homicide rates, right, over time. Okay, by the way, just incidentally, notice that they put this break in the graph. Okay, we'll talk about that later. Okay, but we've got homicides per 100,000 of people over time by year. Okay, so we can see lots of interesting things going on, right? So we've got this rise, and then we've got this up and down, right? Went down here, went up here, and then since 1994, it decreased significantly and then has been decreasing steadily since about 2000. Okay, so there's a lot of interesting things here that would raise questions. You know, obviously, common question would be, well, what caused these to happen? What was going on? Okay, so the graph shows how the homicide rates per 100,000 people had changed since 1960. We see that homicide rates rose dramatically, more than doubling from a minimum around 1962 to a first peak around 1974. It then remained high with some variations through about 1993, and after 1993 it fell dramatically to the year 2000, then stayed nearly constant until a slight drop from 2008 through 2012. The decrease in the homicide rates during the 1990s has been attributed to tougher enforcement of drug laws and a crackdown on gangs. Okay. All right, there you go. Not bad. Again, as I always say, please make sure that you ask questions, okay? Use the resources on my math lab to help you understand what's going on, especially when you do the homework. And go to the tuning center. They're a great resource for you to understand the material. And of course, you can always reach out to me and get help, and I'll help you as much as I can with the material. But again, always make sure that you keep in mind all the other resources you have available to you on my math lab and at the college. Okay. Other than that, you have a great day, and I will talk to you later. Bye.